did yesterday. Okay, so now we're recording and then I'll share the screen. Okay, so lecture 17, lecture 15, circuits. Pretty straightforward. This is your capacitor. This is a battery symbol and then a switch. Let's see. So combinations of capacitors. In practice, two or more capacitors are sometimes joined together. The circuit diagram below illustrate the basic combinations: parallel and series capacitors. Apparently, it's also possible to have things in series parallel or something, where it's like you would have like two capacitors in parallel with two other capacitors in parallel, and then those two are in series or something like that. Maybe we'll see an example. I don't know. There's a potential difference V between A and B. So V is potential difference in this case. So here V is the same in both capacitors. So then Q1 over V. Wait a minute, what? Okay, let's get the whiteboard open.
I don't understand this picture.
When it tells me things like the potential difference V between A and B, and then you give me this drawing, I don't know what you're going for, so
The only part that makes sense in this slide is C equals C1 plus C2.
yeah, that's going to be your rule for parallels. So parallel equation is C equals C1 plus C2. Okay. And I'm pretty sure that okay, let's see. If you have a thing here like this, and then you have A, or well, actually, that's a bit messed up here. This is supposed to go like that. This is capacitor 1, that's capacitor 2. V is the same on both capacitors. I'm going to assume this is, well, potential difference. Which potential difference is what now again? Is that voltage? That's not voltage.
Yeah.
It is voltage?
Yeah.
Shit, all right. Potential difference is voltage. So Q1, charge Q1 divided by, so this is your finding the capacitance. Yeah. Because the equation for capacitance is, let's see if I can find it. See if I can remember it. Capacitance is charge divided by voltage. So capacitance is equal to the charge divided by voltage. So what you're finding here is the capacitance of that capacitor. So that's going to be C is equal to charge over voltage. So in this case, you're looking at, charge at this capacitor divided by the overall voltage gives you that capacitance. And this is actually the general formula for capacitance. So if you look it up, this is what you get. You get Q is equal to CV. Q is your charge. So if you get a question that says, hey, you have a capacitor of this capacitance with this voltage, what is the charge? That's what you're getting there. That's that. Charge on C on this one down here is the sum of total charges. Okay, that makes some sense there. Who's pinging me now? Oh geez, hold on. Someone saying something? No, okay. I don't know who pinged me. Anyway. So the charge on the overall thing is just the sum of charges. And then you could say C is equal to, so capacitance is equal to this. which in this case is equal to charge 1 plus charge 2 divided by V, which that's kind of an extension of this right here. And then it says here you separate them, and then that's just capacitance 1 plus capacitance 2. And that's how that works. This equation is for capacitors in parallel. Increasing the number of capacitors increases the capacitance. Okay. I'm gonna have a question about that earlier, but let's see. The equivalent capacitance here is, I'm gonna go with A. It's gonna be 9, and it looks like capacitance is measured in farads or whatever it's called.
Mhm.
A.
I think that's how I say it.
Yeah. All right.
Farads.
Capacitors in series. This one actually took me quite a while to understand at the time. Hey, Elizabeth, welcome to the call.
Hi, just give me a minute.
Oh, you're good.
I feel welcome.
Yeah. No, you're all good. Oh, yes. There. I was just going to ask about that for the whatchamacallit. We all join in on the oh, if my camera will work.
I don't even have a camera. Sorry, boys.
You
It's
gotta get in
Milo.
on the webcam game.
Who's Milo? I'm Milo.
That doesn't help me.
My full name is Milo.
That's your full name.
Amazing.
Yeah. Hold up.
Pretty cool.
Let me. I can do something.
If this wants to work.
Sorry, I have to help my mom. I'm trying to get her a lift. Now there's 2 Milos.
Yeah, no, what was my iPad so that I can join the face cam group, I suppose.
Yeah, I'm trying to get my webcam to work. My webcam can be a little finicky sometimes. God damn it. There you go. Okay. Now I can't be the only one without a face. It'll work eventually.
Where's the face cam?
Okay, let's turn it off and we'll do that. Let's see. God damn it. Well, hey, 3 is a crowd at this point, so we're doing pretty good. All right. Let's see. Okay, so Elizabeth, you didn't really miss much. We were just going over lecture 15, or lecture number 15, technically lecture 17, I think.
That makes perfect sense.
Yeah, that, just, I don't know.
Is it okay? What's the difference between resistor and resistance?
There we go.
Um,
Okay, resistivity is what you're thinking of.
Yeah, I was gonna say that.
Resistivity is, let me kind of.
Wait, what is?
So
The thing is that I know it in ASL. I just don't know it in English.
Is there like a translator that you could use or something?
Not really. It's just resistor and then resistance. Because this
Okay.
is like
No,
current.
so a resistor is the thing that makes resistance. So when you see like the little dash, not dashes, like the tooth markings on the circuits, one of those is called a resistor, and it has resistance.
Okay.
Oh no, did my camera just die? God damn it. Oh well. I'll figure it out. I don't know. Could that be like a translation issue that you have in class? Because resistivity is a state. It's not a state, but it's like it's a property of a material, So aluminum has the resistivity of, a certain amount, 5, right? And we actually saw this on a recent lecture, the recitation quiz, where it asked if you cut, I don't know, I think it was a copper wire in half, what is the resistivity? And it's the same. because resistivity is a state. It's an attribute, you
It's a
know,
material property.
exactly.
Here, give me 1 second.
Yeah, you're good. Let's see. Okay. I think my camera just like, oh. Okay, it's working again. I'm not
Welcome
gonna
back.
touch it. I'm gonna leave it. So capacitors in series. Pretty straightforward, I think. It's a potential. So here, the total potential difference between A and B is voltage is equal to V1, V2. Well, not volt. Probably voltage actually. So V1 plus V2. Also, so it looks like for this one, series equation is voltage is equal to 1 over C. Now, one of the things with this is that sometimes they'll ask you what is the capacitance or whatever. So with this, some equations, the way you want to think of it is you'll have it like 1 over C total is equal to 1 over C1 plus 1 over C2 all the way to however many capacitors you have in the series.
Sorry, I had to help my mom like get her lift thing situated because she doesn't know how to do that.
Is it lift as in like the app or lift as in the chair lift on a staircase?
Does your mom even lift, bro?
Or lifting as in weights?
Does she lift? No, I don't think she could do that. It's like the app. They're going to the airport tomorrow and I can't drive them because I have to go to the barn. I don't want to drive my parents to the airport.
That's fair. I had my dad had me drive him to the airport at 5 a.m. once, and that was not a fun time.
Yikes.
So,
About the translator error, I don't know, because the thing is that visually I understand this is like resistor. It's like something that contains resistance, and then this is like the resistance through resistor.
it could be that let's see, hold on. It could be that you're dealing with you have an individual resistor which can contribute to an overall system resistance, kind of like what we're doing here in the series circuit, right? So the resistance of C1 can be, I don't know, 5 microfarads or whatever it's called, right? But then if you have, in this case, for example, let's just assume like, so we're trying to find the total capacitance. So let's say that capacitor 1 had a, wait. I'm thinking of resistance. These are capacitors. Let's assume that we're talking about resistors in series.
I think you should probably just wait until we get to that part because I think that's going to be in the things we covered today.
Yeah, that's probably going to be there.
Well, you have an accent. I just realized that.
There you go. So it could be it could be a matter of you're thinking of an individual resistor versus the overall resistance from resistors that are in series or parallel or a systemic resistance.
I think maybe that's where I'm lost because I'm thinking of the individual, but then there's resistivity.
Yeah, again, I think you should just ask me when we get there. There's so many like bar words.
Yeah, resistivity is the property again, right? So if you cut aluminum in half, it's still going to be aluminum, right? So the resistivity stays the same on that one.
Is that like Coke?
No, it's bubbly. Sparkling water. What is that?
Water.
LaCroix.
Oh, my battery died.
Water?
Sparkling water.
I don't drink soda.
This isn't soda. This is sparkling water.
I know. I'm just saying I don't drink soda.
This is much better.
It really is.
So bubbly is just like fake soda then?
Yeah, it's a sparkling water.
Bubbly is Nicorette gum for soda drinkers.
Yum. I actually have friends who are addicted to nicotine, and they're like,
yeah, that was high school. Yeah,
I know, but it carried over, and I don't know how to help them.
Yeah, that was a big thing in high
Like,
school.
could it be me?
Yeah.
Could
No, that's
be-
fair. Okay. Anyway, let's keep
Okay.
chugging along here. So let's see. So the total potential difference between A and B is the V is equal to V1 plus V2. So this is how you would calculate overall capacitance within a system. So if you have the overall the voltage, you can just add them together. Or if you don't, if you have a charge and the capacitance, then you would write it like that, it looks like, plus etc. Q2. And it looks like you keep the same charge too. So that's pretty neat.
Yeah, yeah. If you look at the picture at the top, the leftmost plate
Oh,
is
yeah.
negative Q, and then positive Q, and then negative Q, and then positive Q. So they always alternate. Then yeah,
Gotcha. Okay.
but it is the same charge. Yeah.
Makes sense. Yeah, because it's a charge for an overall system, so it makes sense. And this equation is for capacitors in series. Increasing the number of capacitors decreases the capacitance. It makes sense. I mean, I think of this like you're slicing the same pie, and that pie is the voltage, so you can only, anyway.
Like that.
Yeah, so with this one right here, the equivalent capacitance is, so if we wanted to solve this, so we're going to have it 1 over C total, and then that's going to go 1 over 3 plus 1 over 6. And if we combine these, that's 2 over 6 plus 1 over 6,
Mhm.
right? So
Which
that
is-
becomes 3/6,
Which is 1/2.
which is 1/2, or 0.5, which is,
Yes.
oh,
but
wait, no, it's D. Hold on, I messed up. So a little rule of thumb. Yeah, it's D here, and this is Y. This is 1 over C total.
Yeah.
So you want to flip this. C
Oh
total
yeah,
is 2.
reciprocal.
Yeah. Yep. It's reciprocal and then divide. Inverse of sum of inverses. Yep, that's easy to.
So for series, it's invert. Okay, so capacitance, you have series, which is inverse, and then parallel, which is total. And then for
Hmm.
resistance, it's opposite.
Yeah.
Okay.
For
I think I'll remember
resistance.
that. I might have to ask my interpreters for help on the
Okay.
exam. I'm gonna be like, hey, do you remember this?
Yeah.
No.
If I'm right, well, I guess we'll cover it when we get to resistance, but I feel like with resistors in series, it's the same concept here, is it not? 1
It's-
over.
It's the
It's the
same
opposite.
flip.
Oh, is it now?
Yeah. So when the resistors are in parallel, you do the inverses, and when they're in series, you add them.
Interesting. Okay, gotcha. So here we have 2 capacitors, 2 and 11 are connected in series to a 9-volt battery. So with this one, we have just come up here, I guess. So you have a battery. They're connected in why did it do that? 2 capacitors in series. So this is a 9-volt battery. So we have the overall voltage. Find the equivalent capacitance of the combination 1 over C. So if I'm right here, we can keep in mind 1 over C is also equal to the voltage. Correct?
No, you're missing
Yeah.
Q.
Oh, I'm missing Q. Okay, I'm missing charge. So
Which we don't have.
this has a capacitance of 2 micro F. I feel like I'm doing a disservice if I keep saying it wrong, so I'm just gonna say F.
One of them's 11.
Oh, that's 11. Yeah. 11. So if we want to find it again, it's the same thing here, plus 1/11, which,
13/22.
you said 15/22?
13.
That's 1/c. So and c is equal to 22/13. We don't even get an answer here. Exciting.
Nope.
Okay.
can
Find the
type it.
charge on each of the capacitors. So charge, let's not forget that voltage is equal to charge divided by capacitance. So here we have the voltage, which is 9, is equal to the capacitance, which is 22/13. And then you have Q. So let's say Q like that. That way, you know, it's a Q and not a 9. Then the potential difference across each capacitor. With that one, it would, yeah, like he's saying here. So for the first capacitor, if we wanted to do that, it would just be the potential difference is equal to the overall charge, which would be
9
9
times
divided
13.
by 22/13, like
Yeah.
that. Yeah, wait, am I getting this right? QC 22/13.
Yeah, and so that's V1.
Divided by,
And then you divide by the individual resistance, or sorry, capacitance.
yeah. Q is, so this is Q, and then you divide that by the capacitance,
Right. So
which is
you would do
22.
2 or 11. No, because that's the total.
Oh, you're right. Okay, so this would be, yeah, 2/11, or 2/1, which is just
Mhm.
2. Gotcha. That's a nasty one.
And
Wait,
then
that's divided by 2.
yeah,
Yeah, because this is Q. Oh, geez. This is Q. This is C1. See this formula right here?
Oh, okay.
So this right here, this is Q. So we divide by this, or, oh, wait a minute. No, I messed up my math here.
no, you're good. What do you mean?
No, this should be 9 times 22/13. Because this is Q right here.
Right. Yep, you're right.
So yeah, that's
Mhm.
why multiply. And then for the C1 right here, C1, that's this is C1. So, and if I had 1/C is equal to 1/2, right, for C1 is equal to 2 micro F.
Right. You can just look at the capacitance that's in the circuit.
Yeah.
I'm so sorry to ask this. Where are you
Go for it.
from?
Me,
Yeah,
Colombia.
okay. I couldn't pinpoint your accent. It's just sometimes it's hard for me to understand people's accents. It's
Yeah.
nothing
are-
against you.
You're
It's-
the only person who has told me I have an accent, and I think it might have something to do. I mean, Miguel, should I call you Miguel?
Yeah, you can call me Miguel.
Do you think I have an accent?
No, I just think you have like, it's just like your voice, you know?
Yeah.
I
Then
pick it up
again,
so fast.
here's what I'll say. Maybe I'm biased because I'm Peruvian, so
Oh, okay.
maybe
Well, I
I'm
don't know. I don't think you have an accent either.
I don't
Yeah.
think Miguel has an accent, and that's just me, but I think you have an accent, and it's thick in my opinion. Well, it's just because like,
I mean, that's okay. It's not.
I-
I'm not taking offense. Don't worry.
okay, I'm just like, I don't know, it's kind of ironic because deaf persons accents, like, you know what I mean? Like-
Yeah,
That's
I feel
so
like
funny.
it's something about your that just I don't know, because literally the only person on earth who has said that.
Yeah,
Yeah.
Milo doesn't have an accent. to me.
It's just
but
the
I had a
slightest.
British guy say I had an accent once, and I think that was a pretty existential crisis for me.
Yeah, bro, I have an accent in American English.
Well, I don't know.
I
Hear it.
guess.
It's like the slightest accent, like it throws my mind off.
That's fair. I get that. All right, let's get this started then, I guess.
All right.
Let's keep going.
Oh my
All
God, no,
right.
please no. Wait, scroll back up real quick, just for a second.
This
Yeah,
is a lot
every-
scarier
That looks
than it
like
actually is.
hell.
every single time I look at this picture, it just clarifies everything.
It does.
Yeah, because
good.
if you look at the top, you go 1 + 3, 4. Oh, 4. And then 1/4
Yeah.
plus 1/4. Oh, 1/2. Oh, 2.
Uh-huh.
Like if you look at
That's golden.
if you look at the top, it just clarifies it so well.
You're saying
Yeah.
a lot of things, and I hear you.
But you don't understand me.
Yeah, okay. Let's just kind of move this over like this.
Just
I
copy it.
I remember specifically when the slide came up and my mind checked out.
Yeah, yeah.
Yeah, I remember that too. That was a fun day. Okay, so
Dude, you should just copy the picture.
I
Don't draw
should
it.
have.
Don't draw it.
So I'm just gonna do the top, just
Okay.
like you said. So we have a 4, and then 1 and 3, right? So the way this is gonna work is we want to simplify this this thing, right? So the way it's gonna work is that kind of like PEMDAS. With this, you're gonna say, I need to combine the ones that are in parallel first, because you can't just combine 4 and 3 and exclude the, you can't really do that. So combine the ones that are in parallel. How do you do that? You just add them together. So with the equation that we were looking at earlier for this, capacitance is equal to C1 plus C2. So in this instance, you would get 4, and then it goes 4 again. See, these. I should use a lighter color. Hold on. I like that dark blue, but these combined to this 4, and then you're left with a system with 2 capacitors with capacitance 4, right? And in this one, you get 1 over capacitance. I'm going to say total capacitance. The naming scheme isn't super important, but I just like to think of it. This is the total now. You get 1 over 4 plus 1 over 4. And and then you get 1 over C total is equal to 2/4, or C is equal to 4 over 2, which is just equal to 2. Does that make sense? Micro F. Does that make some
Yeah.
sense? So
It does.
parallel, add, series, the less fun one. So yeah.
I need to get used to the units because I haven't been paying attention to the units in the past like 2 or 3 weeks.
I get that. All right, there you go. I have struggled with paying attention at all in the last 2 or 3 weeks, so
Yeah.
I got that going for me.
It's kind of bad. Like I'm just getting over being sick and I'm already feeling burnt out from all this work or lack
Absolutely.
thereof.
Yeah.
So I get
I mean,
that. But
that's
look,
that.
yeah, we're gonna cruise through this and we're gonna get to the hard stuff and we're gonna review that and it's gonna be totally fine here.
Yeah,
right?
I'm actually. I mean, I'd be super down to just do this like for an hour on the week, like Monday, Tuesday, Wednesday, Thursday.
I'm
it's-
down.
It's really not that bad.
You're
Yeah.
telling me you don't hear the accent?
Yeah.
I
No one
don't,
hears
I
it.
just-
No one
sounded
hears it.
Cursive. You just sounded cursive the whole time.
He just-
I don't even know what you
Sounded-
said.
Okay. It might be that I speak really fast, so I'll slow down.
It's
Alright, there you
okay.
go.
You don't have to slow down that much, but like for a second, I thought you were speaking full on cursive. Another person has
It's a
joined.
very unique perspective, but all right, welcome to the call, Alice. Just so you know.
Oh shit,
Alright.
my mic
What's
is
up?
on. Sorry.
Yeah, what's up?
No, you're good. Feel free to join the webcam gang. We are encouraging the
Sweet.
webcam gang here.
Would you guys want to do these next two problems? I'd prefer to skip them, but if anyone wants to do them, it's not a big deal.
Yeah, this one doesn't seem too bad. This one seems welcome to the call. All right.
Hello.
There
Howdy.
we go.
I'm
So this one
gonna
right
be
here.
cooking on the side, so I'm gonna mute myself.
No, you're fine. You're fine. No worries. So this right here seems pretty straightforward. You just combine these two in parallel. So then you have these in series. And then you're actually kind of in a unique situation where you have, well, combine these in series, combine these in series. Oh, and then you could just add them all together. So actually not that crazy.
That's a dumb question. What do you do with the 8 microfarads in the middle?
When you simplify the left side entirely and the right side entirely, you have a three-way connection. You can just treat that in parallel. So you can just do the left side, one over the left side, one over the 8, and then one over the right side.
Yeah.
Okay.
So yeah, let's just assume that like we did the math for this side and it has capacitance of, I
A.
don't know, 7
You can just say A.
or A, yeah, A. And then you did the capacitance for this side and it has capacitance of B. What you would get is for the total capacitance, you'd get A plus 8 plus B.
Oh, okay.
It's
I get
just in parallel. Okay. This is more questions, more questions. Okay. Let's do lecture 16.
Oh, well, that was it.
Whoa. My light just went off. What happened? There we go. That was weird. Anyway,
Chapter 27.
lecture 16. Yep. 16.
This
Chapter
this is where I checked out.
Okay. I think this is when it starts getting kind of funny.
Man, I took that long ago though.
Oh God, electric field stuff.
Oh, I don't remember this.
Yeah.
I got you. No, I don't got you as in I understand it. I got you as in I understand
Oh,
your perspective.
never mind. I just every time I just know that like the sign all too well for electric field though, because every time Josh signs it, he has like this face and he's like, he always looks lost.
Yeah, this class is getting pretty rough. Hold on. Focus in here. Okay. So the motion of a point charge in an electric field. So, okay. A
Good
particle of mass m and charge q is placed in an electric field and it experiences the force F is equal to the charge times the electric field. The particle will accelerate with acceleration A is equal to the charge divided by mass times the electric field. I'm going to assume that's mass.
Yeah.
Okay. The charge accelerates with that. So in this equation, all we did was we substituted the equation for field. Bless you.
Thank you.
We substituted electric field into that, and that's this new formula. Because I just realized the really easy way to remember the equation for electric field is just say that it's evil. EVL, evil. There you go. Really easy way of remembering it. Anyway, it's not related to anything. It just reminded me. So the conductor and the electric field. So this is if you held up something that has a certain amount of conductivity. There's 24 slides in this.
Yeah, it's gonna be a long one.
We're not
Oh.
going through all 24, right?
Yes, we are.
Hell yeah, we are, brother. Let's get going. All right.
Yeah.
Conductor in the electric field, negative electrons move inside. Negative electrons move inside. Oh, I think he wrote this a little weird. I'm going to say the way I think it should be written, but negative electrons inside the conductor move to accumulate at the surface. leaving positive ions at the opposite surface until the electric field inside is totally screened. Electrons accumulate at the, oh. Wait, there's 3 Milos now?
Don't worry about it. Don't worry about it.
Recording in progress.
Oh my gosh. Okay. If we could just have like a 3-way view of your face as the call goes, I think that would be ideal.
No, unfortunately, only one of my devices. Actually, I guess 2 of them do.
Oh dang, okay. So electrons accumulate at the surface, don't move outside of the conductor because it costs a lot of energy to leave a solid surface. It may happen if the electric field is very large. We don't consider this case. This is kind of like what we talked about in the past about having an electric, like a charge point inside of a conductor. Yeah, the negative particles will go, like if it's in a cavity inside of the conductor, the negative particles accumulate around that inner surface while the positive particles accumulate among the outside. If a conductor connected to a battery, electrons under the field can go through the wires and through the battery. They will not accumulate at any surface. Okay. Now we have this. Conductors are made of materials in which some of the electrons are free to move, not bound to the ions. So a good conductor would be like a copper, I'm assuming, because we use it in everything. So in normal state, these free electrons have random Brownian motion in the material because the electrons frequently collide with ions. And this is an example. This is literally how it is. This is exactly how the electrons move, obviously. I'm going to assume that this right here is assuming that there's no electric field. So actually, we can actually have a little bit of fun with this or whatever. If you have an electric field going down like this, meaning it's a positive charge, this electron would stick to the top part of this box, while positive ions would accumulate at the bottom to counter it, right? And then, so yeah, it looks like in this instance, it's kind of similar. So if you have an electric field moving to the left, it pulls the electron more to the left throughout its Brownian motion.
Brownian motion basically just has, it's just random.
It's just, yeah, random motion. Okay. So I see it here, but gradually drifts in the direction opposite to the electric field.
Yeah, the electric field is going completely left.
Yep. That makes sense. Because it's a positive, like positive is on the right, so it's going that way, and the negative is attracted to the positive, so makes sense. Okay. A model of conduction. So wait, do we have any equations so far that I should copy down? Okay. Electric field. Force is equal to charge times electric field. And then let's remember electric field is equal to volts over L. Oh, that's the distance between both both plates.
It's evil.
It's evil. This is between 2 plates. So it looks like with this, we're going to be mostly working with the electric field within a capacitor. Then we have acceleration is equal to Q over mass times E. Gotcha. Okay. Not bad. Not bad. This is, so far it's okay. So far it's okay. So let's keep going.
The next slide is actually the one that gets horrible. Yeah, this one.
Okay. The graph shows the speed of the electron during multiple collisions. The average drift speed is velocity of drift is equal to E TME. Okay. Now what is okay? I remember reading this and I think I called out to Mr. Stahlbaum. I said, isn't that torque? And he laughed and he said that we are running out of letters to use. So with this, I'm gonna
The
assume.
little e and what is the big E? And
So I'm gonna assume
what is everything?
that little e is the charge of an electron, is my assumption.
Okay.
So let's say average drift speed. So if we were to say this in plain English, the velocity of an electron's average drift speed is equal to the charge of the electron times multiplied. So the charge of an electron multiplied by the time between every collision, the average time, divided by the mass of the electron multiplied by the electric field.
Okay.
And the electric field is the voltage, I think, divided by the distance between two plates. There's a lot.
That only works if you're talking about plates, but yeah.
Yes. Okay. Slash model of conduction. Okay. So VD is equal to E T M E. T is mean time between collisions. Okay. So what this graph is saying okay. So line goes up, but line no always go up. Sometimes line go down. And line always go up again after down.
I think this is okay to skip. We haven't come across
Yeah.
anything like this in a while.
Okay.
And then
Oh,
it just jumps to a different topic entirely.
yeah, that's what it looks like. All right. Electric current within a wire. So DQ passes through a ring inside of a wire. So the definition of electric current as the movement of charge across a given area per unit of time. So the electric current is a movement of charge across a given unit. So current is I is equal to dQ over dt. The SI unit of it is that capacitance over seconds?
Charge.
Charge.
Lumps.
Coulombs. Yeah.
Coulombs. Okay. Yeah, capacitance doesn't make any sense, right? Because capacitance is also a property of a capacitor. So that doesn't. Coulombs per second. Makes sense. Also denoted as an amp. And so the average is also the change in charge over the change in time. So that's if you're looking over a period of time. The direction of the current is the direction in which the positive charges would move. Electrons move opposite to the direction of the current. Okay. Electrons move in opposite direction. The actual charge carries electrons. Move. The actual charge carries move one direction, but current is defined as motion of charge to opposite direction. Very confusing. However, all current related effects are the same. Okay. Sometimes you could. I love how he just puts very confusing. So with this, every minute, 120 coulombs of charge flow through this cross section in a wire. What is the current of the wire? So we could go using one of the equations we saw earlier, which was I is equal to the change in charge divided by the change in time. If I'm right, charge is something that's usually denoted in seconds, not minutes. So with this, I'm going to assume we'd say 120 coulombs over 60 seconds. So I'm going to say that this is 2 amps. And it looks like we're right. So there we go.
Yeah.
Watch out, NASA. Here we come. All right. Anyway. Current density. This is a funky one.
Oh shit, I forgot about this one.
If current I flows through a surface A, or in this section, let's just instead of surface, let's say wire, the current density J is defined by the current divided by the area of the cross section. So J is equal to the current divided by the area of the cross section. Does that make sense? It's that little area. Okay. The current density of the wire is, what is the current density? So in this one, we have 8 amps flowing through. So let's just kind of get this one done. So charge density is equal to I over A. So if I'm right, this should kind of be denoted as amps per, oh, he has it here, amps per meter squared. So this is going to be 8 over 4 millimeters, centimeters, 4, like that. Like that.
2 times 2 is 4, and then divide by 1,000. Yeah, I agree.
Yeah, right.
That should be D, I think. Or B.
Yep, it's D. 2000 amps. Oh my God. Wait. 2. Amps
That's a lot.
per meter square.
I
Oh,
think that's a
okay.
lot.
Here's why it's a lot though. The size of the wire in this case is only 4 millimeters, and we have 8 amps flowing through it. So if you brought it up to a meter, I'm assuming what's a if we multiply that by wait, I'm trying to like, so if you're talking about in terms of, yeah, 0.004 meters has 8 amps, I could see it being D, because if
Okay, I think we just did the math wrong.
it's
I'm sorry.
actually more. Am I doing the division?
I think
right
it's like the conversion,
Yeah.
like millimeters.
here? 0.002 times 0.002.
Like 0.00.
Oh, it was the conversion.
Yeah.
Because what I did was I multiplied the 2. I did 2 times 2. That was 4. And then I just did, oh, it's millimeters. And so I did point, like right here, 0.004. That is not right. That is not how you do it. The way you have to do this first is you have to come in here and you want to say 0.002 times 0.002. That's the important part. And so then you get 8 divided by 0.00004.
Oops.
And that gives you 1, 2, 3, 4, 5, 6, 2 times 10 to the 6, or 2 million amps per meter squared. So if you had a copper wire that was a meter thick, you could deliver 2 million amps of electricity or of current. Let's Google something. How
Wow.
many amps needed to kill a human? I mean, I guess it
Okay.
depends on.
A human.
I mean, I think that's not going to be a very accurate result.
I guess it depends on the voltage as well, but
Yeah,
according to-
exactly.
According to OSHA.gov, oh, it's a PDF. Where is it? Introduction to electricity. So here it's the little highlighted answer is that 10 amps is enough to induce cardiac arrest and severe burns with probable death. We're doing 2 million. So if we divide that by 10, that's enough to kill 200,000 people in one go.
Now, I
Every
don't want to
second.
say this, but if we all hold hands, then we would act as resistors. So it could do a lot more.
Because our skin has resistivity to it. So there you go. Bringing it back to an old conversation. Anyway. See, this is the kinds of things we need to be learning in class. How many amps do you need?
You know, people would learn this material quick if they like correlated it to real
With
life.
murder.
I mean, that too.
Yeah. All right. So here we have both segments of the wire that are made of the same material. You have a current flowing through the first segment. How does the current I in the segment compare to the current I sub 2 in segment 2?
It's the same. I don't know
I'm
why.
assuming it's the same. Because
But
if we keep in mind,
Miguel, could you open your Zoom settings and turn on your thing again? Remember how last time I told you that you were
oh, the noise suppression.
that. Just put it back to what it was, because now Elizabeth is like super loud in comparison.
I'm loud.
No, it's not your fault. It's Miguel's fault. Automatically
Oh,
adjust
could
microphone volume.
What if I like brought the microphone closer like this?
You
and
can
then
click the one button that says automatically adjust
Oh,
right below input level.
all right,
there you
there we go.
Perfect.
Okay. Okay. I'm gonna say that the current is equal because current is not, I don't want to say bound, but the formula for current is not having anything to do really with area. So even in this case right here, I'm going with B on this one. Now, the current density.
No, don't talk
will-
about it. That's literally the next slide.
Later on. We'll do that later on. Anyway, let's go.
Yay.
All right. Both segments of the wire are made of the same metal. Current I flows from segment 1 to the left. From the left, how does the current density J1 in segment 1 compare to the current density J2 in segment 2?
1
Current-
is greater than 2, I think.
I agree.
Yeah, 1 is greater than 2. There we go.
First time
Um,
in physics.
do we know by what order of magnitude it's greater than? Is it double? Well, I guess we don't have a fixed number here, huh? Never mind.
Well, my reasoning is that it starts from the left, and from the left is 1, and then it goes to 2.
Yeah.
So
I'm gonna assume that there's a linear correlation because it's just I over A. So if area doubles in size, you're having the charge density. Right? So,
Yeah.
that too.
So a simple model of current by Drude 1900. Okay, after each collision of an electron with an ion, it will accelerate under the electric field with acceleration equals charge of an electron times the electric field divided by the mass. Suppose the average time between collisions is that. Then the average velocity is that.
This
charge
is the
of
same equation as earlier. I'm gonna
Yeah.
die.
That's what I was getting at here. It's E T M. Yep. Electron drift. This is when we were talking about the speed of an electron drift within within a wire. He was saying something along the lines of there's a reason that it doesn't take me a week to turn a light on when you flip the switch. I guess we'll kind of see what he was talking about.
The story that I forgot about.
Is that the one?
I remember that discussion in class, but I wasn't paying attention. I think my years were lost too.
Oh,
So
gotcha.
they got lost in translation. So Josh was just like, and I was like, okay.
Amazing. So with this, the density of electrons in N and the number of electrons in time t, all the electrons in the cylinder move out through the right end. So in this case, there's like a flow. Hence, the charge per unit of time, the current, is I is equal to the number of electrons times the charge of an electron divided by the change in time.
Right, because the charge would be the number of electrons times the charge of each electron.
Makes sense. So this is the, what are we finding here? This is the electron drift velocity.
We were trying to find
Like
an
this
expression
formula.
an expression for current.
Okay. And so current density is, so I feel like we're just kind of restating what we just went over. But it looks like we're kind of decomposing it more because here we put in the formula for the N. And here you have the charge of the electron.
So little n is the density,
Yes.
and then
So
the n is like the number.
yeah, so in this case, you have I over A, which is the density of electrons times the amount that the electron charge times the average drift formula, which is, as we talked about, it's the E times the average time of an electron collision divided by mass times, it's this right here, times the electromagnetic field. Wow.
Hopefully that's not on the test.
If just get the equation and you'll be good.
Yeah, so that's right here. I'm just gonna write J is equal
It's a
to
lot.
Yeah, it's way too much.
But he's
I over
really
A.
nice with the test. Maybe that's just me.
I agree. It wasn't bad.
No, but I didn't really study for it. So. I could have done better. I could have done a lot better if I actually studied for it.
Okay. Wow. I love like the differing font sizes and colors.
It's so bad.
and-
It's so bad. But I feel like he does these every single day before class.
There's no like spelling errors. I could
There's so many grammatical errors.
There's a few grammatical things in there, yeah.
It's okay. My life is like one big grammatical error. So like I understand this.
Yeah, exactly. Alright.
I don't want to do this. This is literally just plugging and chugging. But if
It's
you wanna
plugging
do
and
it-
chugging.
Yeah.
Yeah, I could see that, because here you're given diameter and charge. All you really have to do is this right here. This right here is all you really have. If you wanted to calculate, yeah, electron drift, that would be the, what do we have here? Oh, I guess another way of doing it is just J over NE. Okay. Interesting.
Ooh.
Much less than 1 millimeter per second. Okay. Anyway.
If we
Ohm's law.
switch on the light, why don't we need to wait for weeks until electrons come from a source to the lamp?
Because magic, man. That's why. It was that was a fun day in class. I'll never forget this.
I can never tell when he's joking. He
No,
starts.
I think I'll be honest. I feel like I don't struggle too much with this accent all that
Same.
much because I have 2 Peruvian parents. So accents is kind of something I've been used to for a while, maybe. So I hear him talk. I'm like, oh yeah, he's like, you know.
You're like the first person that said that, because like everyone else is like, I'm so lost. And because like my
Yeah.
interpreters wanted like feedback from people. So they're like, do you understand this, man? And they're like, no, not a word. And they're like, okay, good to know we're on the same page.
Gotcha. He's, yeah. I mean, I don't know what to tell you.
sound
That's a
like-
hard one.
Like to me, I don't know. He just like, he sounds like if you were to take a pillow and like muffle him, like
Does
put
it?
it over his mouth while he's speaking. That's literally what he sounds like to me.
Does it sound like the parents from
From
Charlie?
Charlie Brown.
blah 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 blah?
Yeah.
Yeah, that he does.
Well,
He's like, wah,
You know.
wah, wah, and I'm like, ha, ha, ha. Okay. Whatever. Whatever
that'll
you
happen.
say.
That'll happen. All right, we found that J is equal to that. So the charge density is equal to that, meaning that the charge density is proportional to the applied electric field. Okay. Charge density.
Oh, I
Proportional.
remember this PowerPoint because you said sigma and I lost it.
Yeah, isn't that sigma?
Yeah,
Hmm.
you just said sigma and I lost it. Like, I
You
don't
know, because I always get between sigma and sigma anyways. So like I never
Yeah.
get it. Yeah. Anyway. Meaning that current anyway, let's see what we got. Damn it, my battery died again. All right. Camera break, I guess. Okay. Found that. No, the second row in this class is so much fun because we just sit there and like a new thing comes up on the slide and like the 3 of us in that row we're like, what the fuck is that? It's just like really crazy.
It's so bad. I lose my shit when I sit next to you and that girl. Like
Yeah.
I can't be serious. Like you say like one thing comes out of your mouth and it's funny as shit. It couldn't, it's not even like funny, but it's like it's funny as shit. Like
That's good. I'm glad that class can at least be somewhat entertaining, you know.
Yeah.
But anyway, Ohm's law. So J is equal to sigma times electric field, I guess. Wait, oh, so sigma is the conductivity. Okay, so sigma is the conductivity. Alrighty. So then with that, we have sigma is equal to the charge, not the density of electrons times the charge of an electron squared times the average time between collisions divided by the mass.
You're never going to know that.
That's
Remove
good,
it
at
from your
least.
brain and like,
Okay.
accept it.
So it is useful to consider the inverse quantity, resistivity, which is denoted as rho is equal to 1/sigma.
Oh shit. I did not know about
This
that.
is when it starts getting a little wacky. So sigma and rho depend only on the material, not its length or area. There you go. So this is the important part, because resistivity is a property of a material, right? However, the shape of the conductor may determine important current related properties. Consider a metal rod of resistivity rho. So this rho rod has an area of A. It has a charge of 0 volts. It's a certain length, and it says the electric field is equal to rho times charge density.
I'm so fucked.
So rho in this case is resistivity. Which is 1/sigma. And then this is charge density. No, it's easy. It's easy. Think of it like this, right? Your electric field is a road, right? What is the material of the road? You know, let's say it's sandpaper, right? This sandpaper has a certain like resistance to it, right? Like the friction force that you can get from sandpaper is a lot more than glass, right?
Mhm.
So sandpaper in this case has a higher resistivity of it. Now, what is the density? How closely together are these pieces of sandpaper, right? Is the whole road covered in the sandpaper, or is it just one little, is it not a lot, right? Is it, you know? And so if it's a lot of fucking sandpaper, and it's all densely packed together, you're gonna have a strong electric field, right? And that, yeah.
It's like electric field depends on charge density.
The formula for the electric field is well, I only have the formula for the electric field between two plates. But what that is that is like the voltage of the two divided by the distance between the plates. Let me see if there's like a more universal formula.
I do want to mention that the reason that in this example we can use the voltage divided by the length is because we're considering a wire. And the only way for a wire to get a current is if there is an electric field being passed through the plates, which would be the EMF. So like a battery.
Mhm.
It looks like, according to OpenStax, oh, what's this? Oh, wow. Okay, so according to, look at this. This is actually pretty cool. They have I remember doing these when I was a kid. These FET simulators. So this is a positive charge. You can kind of see how the electric field adjusts as I move it around.
Ooh, pretty.
And then this is going to be a negative charge. And so you can see how it kind of curves the electric field around it. And so the voltmeters. Oh, can I zoom this in? Is this too small for you guys?
I could see it.
So voltage strength is getting larger as I get closer to the positive charge. And then as I come over here, it gets increasingly negative. So it looks like 0 volts is about here. It's in the middle. This is the weakest, I guess, point between the two charges. And then this is a sensor. So this sensor kind of points like which way the electric field is going in that area. See, so in this one, the electric field is very in that direction. So you can kind of see how, anyway, that's fun. So yeah, so it looks like for this one, metal rod, so the voltage across the metal rod is the current times the resistivity or resistance. No, wait, what is this?
I think it might be resistance because
Charge time
The
by area
E or rho is
multiplied.
I think R is resistance.
Yeah, wait, voltage. Yeah, I think, yeah, R is resistance. So multiply both sides by capital L. You have charge or current there. Oh, so resistance is just equal to the resistivity times the length divided by the area.
Okay.
So R resistance is equal to the resistivity times the length times the area. Gotcha. And so this is replaced in this. So you get V equals IR. I'm just gonna copy this down here. I'm just trying to.
Give me 1 second.
You're good. Anyway, Ohm's law. So the macroscopic form of IR is the most commonly used form of Ohm's law. R is the resistance. It depends on the material type and the shape. So resistance is denoted with the symbol ohms. So rho is equal to this. This is just you throwing it around. So this is the unit for resistivity. So if you're given the resistance of something as well as its length and area, and they say, what's the resistivity? Just flip rho and resistance here and you're golden, right? So resistivity is denoted in ohm meters. Okay.
That's just the table of resistivities.
So a portion of nichrome wire of radius. Do we want to do this question? That's the end of it. We made it all 24 slides. Just so we know. But
Yeah.
I say here, we can shotgun this one. Check it out. We have a tube.
All right, let's do it.
Here we go. Tube. No, let's make it a little bit bigger. So we have a tube. Like that. Tube. Radius. 2 millimeters. Is to be used in winding as a heat coil. If the coil must draw current, so we have current I is 8.5 amps. And the voltage is 120 volts. Find the following. So the resistivity of nichrome is 1.5 times 10 to the negative 6. So what is the resistance of the coil? So R, let's not forget, is equal to, we can actually denote this as volts over current, as denoted with this formula. So all that is gonna be 120 divided by 8.5. We thought this was gonna be hard. Look at this, 14.11. And that's gonna be ohms. Then the length of the wire you must use to wind the, what? The length of the wire you must use to wind the coil.
So it's just saying find length.
Find the length. In this case, it's the same thing. We can use a little bit of a more complicated formula for resistance or whatever. We use the R is the rho length divided by area. So if we were to solve this symbolically, this is going to look like L is equal to RA over rho. And so resistance we have, area we can find, and the resistivity is given. Resistivity is this right here. So all this is going to be, it's going to be 14.11 ohms times the area. I'm not going to make the same mistake here. So we're going to say area is equal to area of a sphere is going to be 5 times 2. No.
0, 0, 2.
That's the area of a circle, right? Am I remembering this right?
Pi r
It's not
squared.
2 pi r squared.
R squared.
It's just pi r squared. Okay.
Yeah.
Look at me. Look at me. Still physics 2. Can't remember the. God damn it. Anyway. This is 1.2 times 10 to the negative 1, 2, 3, 4, 5. So the area 1.2 times 10 to the negative 5 meters. And then you have the resistivity, which is ohm meters. And funnily enough, if you solve this symbolically as well, if you're never sure if you're right, look at it symbolically. You have ohms times meters squared divided by ohm meters. Ohms cancel, meter cancels, you're left with meters. That's going to be your length, right? And so in this instance, I guess let's plug it in. So we get 14.11. 1.2 times 10 to the negative 5.
It looks right, though.
It do, don't it? All right, let's see, 10 to the negative 6. This is a length of 112.88 meters. All right.
Seems right. I feel like we don't need to fact check
That's
that.
pretty good. I don't know. I'm just a student. Anyway. Any questions? Anything?
Nope,
Any
that was really
questions?
good.
Alrighty. I will say it is now 10-ish, 9:55. I'm starving. So would you guys be down for a study session
Dude,
to
I'm down
continue?
any day, every day.
Okay.
I can do tomorrow.
That's
And-
good. I will say, tomorrow is my birthday, so I may not do tomorrow.
Day.
Thank
Bro,
you.
why don't we go over, bring you some cake, we'll sit down and then study.
Do some physics, yeah. Tomorrow I'm just kind of, it's gonna be a day to chill for me. Would Saturday night work for you guys by any chance?
Yeah.
Probably.
All right, and we can continue on, keep chugging forward. That way, when it's test day, we're gonna be fucking
got this.
masters. It's gonna
By
be
the
amazing.
way, what like lectures are on the test?
Everything before lecture 14, I think.
I
It's
think it
so
was
much. It's so
26
much.
through 29. I think is what it was, or
I
something
think
like that.
that sounds about right.
Someone
Chapter
had
Yeah.
lectures.
posted a screenshot, so let me see.
So wait, lectures or chapters?
Okay, Elizabeth, you don't call me out in the Discord either about the corrupted Zoom session. No, it is chapters 26 through 29, and then exam 3 is going to be chapters 30 through 34. So everything that we've been going over the last 2 days is not going to be on the test. So
Okay, no, wait, why not? I thought this was chapter 26.
no, from the last 2 days, that was like chapter 30
Oh, I
stuff.
thought you meant like us in the Discord. And
Oh,
the
no, no, no,
Zoom.
no.
Oh.
Study
Yeah, yeah.
sessions, yes, that is going to be on the test, but in class,
Yeah.
presentations, no, that's not going to be in.
Okay.
So like, what did we go over today, for example? Like if we look down at lecture 29, which was yesterday's, yeah, this stuff, Faraday stuff, the law of induction, this is
Oh,
not on the test. It's on the
Thank
next one.
Thank God, because I did not pay attention in class today either.
That's
lost cause.
valid. Anyway, so I'm gonna stop recording here.